Hi, in this video we'll be talking about basis, which is a very important concept when it comes to a vector space. So let's first define what a basis is. So a basis is a linear independent set that spans the space V. And so you can really think about it from our previous video that it is the minimal spanning set. Or you can think of it as the maximal linearly independent set. And so the space V is a finite dimensional if it has a finite basis. So we let F be a subfield of the complex number, then F3 is the vectors as the following. And this is linearly dependent since 2a1, this linear equation holds true. And the vectors E1, E2, and E3 are linearly independent. So this doesn't form a basis, but this does. And if you let F be any field, and if Fn, then the set of these E1s to En will be known as the standard basis, since they are linearly independent and they span the entire Fn. So this will be known as the standard basis. And so we present a method of finding whether a set spans the whole Rn first, and that is basically arranging the vectors in terms of columns of a matrix. And because when you create the system of linear equation, you see that the vectors form the columns, and it is so what you need to do now is use Gaussian elimination and check whether if a row echelon form does not have any zero row, then it's always consistent. And if it has at least a zero, then it's not always consistent, so it cannot span. That actually reminds you of the previous question we have already done 2 videos ago. So this is like a recap of how to quickly show whether a set of vectors span the entire Rn. And we can extend this on to saying for a general finite basis, you let P be a intervertible n times n matrix. Then the columns will form a basis for this space, column space. So we see that it follows. If X is a column matrix, then Px equals to x1 P1 plus all the way xn Pn. So then since X is equal to 0 as only the trivial solution, since P is invertible, then it follows that this has to be a linearly independent set. And why does it span Fx plus times 1? Well, we let Y be any column matrix, then X can equals to this, then Y will equals to Px, and that is Y equals to this linear combination. And so these columns would then form a basis for F n times 1. So I hope this is clear on why does it form a basis. And with that, we have a theorem and properties of basis is that if V is spanned by a finite set, then any linearly independent will still be finite and cannot have more elements than n. So a proof of this is to show that every subset which contains more than m vectors will be linearly dependent. So let F be such a set, so it has n vectors where n is less than m, is more than m. And since B1 to Bm spans V already, then there will exist some scalars such that Aj equals to some combination of these Bi's. Then for any scalars here, we form a linear combination of this alpha 1 to alpha n. You can just sub in this each alpha j as the following linear combination of the beta i's and form this double sum. And since n is more than m, we know that they are scalars such that not all of them will be 0. And so this shows that the set will be linearly dependent. And one of that lemmas could be that it's called the exchange lemma, is that if X is spanning and Y is linearly independent, then there can exist a subset of this spanning set which has the same amount of vectors as Y, such that X complement X prime union Y will still span V. And this is in particular shows that the number of elements in the spanning set will always be more than the number of elements in a linearly independent set. And so a corollary is that if V is finite dimension, then any two bases will have the same number of elements. So since V is finite dimension, it has a finite basis, and by theorem 4, because if you have another basis, because it's linearly independent and this set is spanning, this set must have more or equals to the number of elements of the other set. But then you can exchange the role, and the other direction holds true as well, and hence they have the same number of elements. So I hope it's clear from the previous theorem and lemma. And so this allows us to define what is a dimension of a finite dimension vector space, which is the number of elements in the basis. And we denote it by the dim V. And so another corollary from our theorem 4 is the reformulation, which says that if you have a finite dimension vector space n and its dimension is n, then any subset which contains more than n vectors will be linearly dependent, and no subset which contains fewer than n elements can span V. So if the basis already has n elements, then if you have more than n elements, then you cannot be linearly independent. And if you have less than n elements, then you cannot span the entire V. That, if you think about it, intuitively, it's like you have R3 and you only have two vectors. Then you cannot span the entire volume. Because every vector, your two vectors can only span at most a two-dimensional plane. And so with that, it comes a lemma which states that if S is linearly independent, then suppose B is a vector which is not in the subspace spanned by S, then the set obtained will still be linearly independent as well. And this lemma is what we have already shown in our previous video. So do check that out if you wish to know the explanation and intuition behind this. As for theorem 5, we say that if W is a subspace of the finite dimensional vector space, then every linearly independent subset will be finite and is a part of a finite basis for W. So it means that if you have a finite dimensional V already, then W will also have a finite basis. So W is also finite dimensional. And suppose that S0 is linearly independent subset of W. If S is a linearly independent subset of W that contains this S0, then S is also a linearly independent subset of V. Since V is finite dimensional, S cannot have more than the number of elements of V. And so we can extend this S0 to a basis for W now. And if S0 spans W by doing the following. So we want to extend S0 to a basis. We just say if S0 spans W, then S0 is a basis. We are done. If it does not span W, then we can use this lemma where we just add on another vector to make it retains the linearly independence, but now it spans a larger dimension. Then if it's now spanning, then it's a basis. If it's not, then you just continue the process. And we can do so in not more than the dimension of V, since this linearly independent set cannot have more elements than the whole V. This shows that this will reach a set that spans the entire W, and this will form a basis for W, and it will still be finite. So W, a subspace, will still be a finite dimensional vector space. And a corollary is that if W is a proper subspace now, then its dimension must be strictly less than the dimension of V. And for this, I'll just leave it to you to read the proof, but it should be quite intuitive. Some remarks to note is that every vector space has a basis. Even though here we are dealing with finite dimensional and we're talking about the basis and whatnot, we can actually show that every vector space has a basis by using the idea that it is the maximal linearly independent set or the minimal spanning set in a clever way of using Zorn's lemma. And a corollary of that, another corollary is that if V is a finite dimensional vector space, then every linearly independent set is a part of a basis, meaning that if you have something linearly independent, it must be less elements than some basis, but it must be from the basis vectors itself, can be formed from the basis vectors. And corollary 3 states that if A is a matrix over the field, then you suppose that the row vectors form a linearly independent set. Then A would then be invertible. And the proof follows because if alpha 1 to alpha n is the row vectors of A, and you suppose that W is spanned by these vectors, since alpha 1 to alpha n is linearly independent, the dimension of W has to be n. And so by corollary 1, it now shows that W equals to Fn. And so there are some scalars, Bij, such that this standard basis equals to a linear combination of alpha. And thus the matrix B with entries Bij will satisfy this following equation, where BA equals to I. And this shows that A must be invertible now, because this is the inverse. And so we have a theorem that we shall now prove to continue practicing our ideas and intuition behind having a basis, is that if W1 and W2 are both finite dimensional subspaces of a vector space V, then W1 plus W2 will still be finite dimension, and its dimension of W1 plus the dimension of W2 will be the dimension of W1 plus W2 plus the dimension of the intersection. So another way of rephrasing this is saying that the dimension of W1 plus W2 is the dimension of W1 plus dimension of W2 minus away the intersection. And so you can really think of it like a Venn diagram. So this is W1, this is W2. If you want to take the whole dimension, it's just like W1 plus W2 minus away the intersection, because you double counted. And so the theorem really follows because you double counted the parts where they are spanned by the same vectors. So first we say that the intersection will have a finite basis, alpha 1 to alpha k, and it must be part of the basis for W1, and it also must be part of the basis for W2. So the subspace W1 plus W2 now can be spanned by the vectors alpha 1 to k, beta 1 to m, and gamma 1 to n. And these vectors form a linearly independent set, since this is a basis and this is a basis. And this shows that the gammas, the sum of these gamma belong to W1, and because they also belong to W2, it must follow that it can equal to some set of alphas. And because this is independent, then the scalars must equal to 0. And so you can reduce it and show again that the whole set is linearly independent, forming a basis for W1 plus W2. And so by just counting the number of elements, we show that the number of the dimension of W1 plus dimension of W2 must equals to k plus m plus k plus n. And really, k plus m, you can group them together to get the dimension of the intersection. And then the other side, you got k plus n, which gives you the dimension. So k plus m plus n, this thing will give you a dimension of w1 plus w2, and k itself is the dimension of intersection. So this relates to here, and this relates to here. And this proves theorem 6, because now you have shown that the dimension is finite dimension from here, and the dimensions are related by this equation. So now I hope you have understood what is a basis, and in the next video we'll be talking more about this basis and how we play around with it for linear transformation purposes. So I'll catch you in the next video where I talk about linear transformation. See you again. Bye.